In the last video, we set up limits and homing for the LinuxCNC machine. As long as LinuxCNC is in control, then we expect that the machine can't hit its mechanical limits. However, watch what happens when I boot up the computer. Random movements? That's not what we want. Oh dear, I wasn't even expecting that. I actually briefly forgot which switch turns off the motor driver here. This was the second take I made for this section. In the first take it did something a bit different and didn't crash so dramatically, but I kept this one because it shows how unpredictable the machine can be when LinuxCNC is not in control. The reason this happens is that the parallel port output pins are not well defined during boot, and often pins will change in what looks like a random order, but it's most likely the computer just probing for a connected printer. In this case there was no damage, but imagine how dangerous this situation could be if we have multiple axes, a spindle that randomly starts at speed, or if we had our hands inside the machine envelope where the PC randomly reboots. LinuxCNC has a solution to this though. We can define one pin as a charge pump pin, and this pin will be changed on and off at a configured frequency whilst the machine's on. So we could check in our hardware that we can see that frequency before we enable motors. We also want to consider LinuxCNC's enable-disable state. That is, LinuxCNC can be in control, but requesting that the motors are disabled. While we are considering safety, it would be a good idea to add a physical emergency stop switch too. According to ISO 138502015, an emergency stop must avert actual or impending emergency situations arising from the behaviour of persons or from an unexpected hazardous event, and it must be initiated by a single human action. It must override all other functions in all operating modes of the machine, and it must be actively reset, and until it's reset, the machine cannot be restarted. Also, resetting the e-stop state must not start the machine up again. It should only allow the machine to be restarted. Let's put together all of these requirements. We need a way to check if there is a certain frequency on the charge pump pin, and that tells us that LinuxCNC is in control. We need a way to check that LinuxCNC wants the motors to be enabled. We need a way to respect the hardware emergency stop and report it to LinuxCNC. We need a way to make sure that when we release the emergency stop, the machine doesn't start up again. And ideally, we also need a way to check that LinuxCNC has acknowledged our emergency stop. Let's start with checking for the charge pump frequency. The LinuxCNC wiki has an article on this, with a few alternative approaches. I've tried a few of these out to decide which one I prefer. The one with the tone detector does work, but when the circuit is first powered on, it acts like it can see the target frequency for a few moments. And while we could work around this, it's also using a relatively rarer component, and we'd have to pay a bit extra to have this manufactured. Doing this with a microcontroller adds some software here, which makes it a much more complicated component. However, we would have a lot of flexibility this way, so I wouldn't dismiss it completely. And it could be done with an Arduino or other off-the-shelf module, so we wouldn't have to build anything from scratch. The one I'm going to use is this one now. It's relatively straightforward and uses cheaper components. It works by blocking DC here using this capacitor, and charging this capacitor and allowing it to drain off through this resistor, which we'll make variable, since that controls the frequency that enables the output. These Schmitt inverter gates are provided by an integrated circuit that contains 6 of them. However, it looks like only these 3 gates are strictly required for this to work, so we can free up these other 3 gates to potentially use elsewhere. I'm also not going to use an optocoupler here. I'll just use an N-channel MOSFET instead to keep the current draw on the pin minimal. Because my logic is all at 5 volts already, and I take logic power from the PC's USB port, there isn't much value in galvanically isolating the input, and all it would do is add latency. Checking for the enable state is an easy one. We can just read the amplifier enable pin value in our hardware. By default, it's true whenever LinuxCNC is in control and the power on button is pressed in the UI. This emergency stop button is a double pole single throw switch, so we can use one of the poles to notify our new piece of safety hardware, and the other pole to notify LinuxCNC. Because our safety hardware is quite critical, I'd rather make the input to it active low, because that way if the e-stop button isn't connected or the wire is cut, it will be as if it's pressed permanently. We can solve the requirements to make sure the machine doesn't start when the e-stop is removed, and make sure LinuxCNC acknowledges the emergency stop simultaneously. Logically, we want something like this. We have 3 inputs here: whether the e-stop is currently pressed, whether we are receiving a valid charge pump signal from LinuxCNC, and whether LinuxCNC has enabled the motor. And we have two outputs. We have gate, which is the main output. When this is true, the motor should be enabled. And lockout, which indicates that an emergency stop state has not yet been cleared. Assuming normal operation, when the charge pump is present and the enable signal is true, the gate output is true. When we get an emergency stop signal, the gate output goes false and the lockout output goes true. However, setting the emergency stop signal back to false again does not re-enable the gate output. The only way to re-enable the gate output is to first switch off the charge pump and disable the machine. Now the lockout output goes to false, and it is possible to enable the gate output again by restoring the charge pump and re-enabling the machine. This is achieved using an SR latch, which gives us a single bit of memory to store the lockout state. In this way, we are able to make sure the machine doesn't start up again when the e-stop is reset, and acknowledge that LinuxCNC saw our e-stop, because the only way to start back up is for LinuxCNC to go through those state transitions correctly. I also want the safety module to start up in the lockout state, if enabled or the charge pump are present, and this way power cycling from the safety module doesn't bypass the lockout state. Adding that as an additional input leads to this logic. This uses quite a lot of different components. We have 3 AND gates, 2 OR gates, 2 NOT gates, and an SR latch component. We can get ICs with multiple ORs, ANDs, and SR latches, but if we do that and send this to manufacture, we'll get charged a pick and place fee per component type. So it would be better to have as few unique components as possible in our design. If we look at how an SR latch is constructed, it's either 2 NOR gates or 2 NAND gates plus 2 NOT gates. So it would seem like the NOR way is less components. But if we add in the rest of the circuit and convert all of the gates to equivalent NOT AND and NOT gates, we get quite a lot of double inversions, and these just cancel out. Now we have 7 NOT AND gates, which will be 2 quad NAND ICs with 1 spare gate, and 5 NOT gates. We could convert any of those gates to single NAND gates too, but I'm going to hold on doing that until I've integrated it with the rest of the circuit, because we have that one Schmidt-Trigger inverter IC for the charge pump detector already, and we know we can spare some of the gates on that. Here's a circuit I ended up with. This section is a charge pump detector. As you can see, I only used 3 Schmidt inverters for this. I made this resistor variable to add some control over the triggering frequency. This section handles the logic for e-stop, enabled, and lockout. These are the inputs. I used the remaining inverters and some N-channel MOSFETs for inversion when I ran out of those. When designing this and other circuits, I make sure that every output from the parallel port goes directly to the gate of a MOSFET or the high impedance input of a logic IC. This way I limit the amount of current required from the pin. This section handles the gate output. I decided to provide the output in the form of a double pole double throw relay. This is a really flexible form of output. I can use it to switch 2 circuits at different voltages or different ground potentials if necessary. Finally, these sections are the connectors and the power sections of the integrated circuits. I ended up with just 3 ICs, that's 2 quad NAND gates and 1 hex Schmidt inverter. I built this onto a breadboard to test that it works, and I'm going to connect it to the correct pins of my parallel port. This area detects the charge pump, so we'll connect that to the charge pump output here. The amplifier enabled output pin connects here. The normally closed pole of the emergency stop switch is connected to the safety module, and the normally open pole of the emergency stop switch goes to the e-stop input parallel port pin. This way LinuxCNC sees the e-stop event at the same time as the safety module. The gate output connects to the enable pin on the motor drivers. The way these work is if there is a voltage applied, then the motors are disabled. So we connect the normally closed relay pin to 5 volts, the normally open pin to ground, and the common pin to the motor driver enable positive pin. These LEDs show the state of the system. This red one shows the emergency stop status, and this one shows the lockout status. The first yellow pin shows the charge pump status, and the second shows the enabled status. Finally, the green LED shows the gate output. Now everything is connected, let's try booting the computer up again and seeing if we still get random movement of the axis. As you can see, the computer is sending enable outputs, but no charge pump, so there's no movement of the axis. When we open LinuxCNC and disable the e-stop, you see we do get a charge pump signal. And now when we enable the machine, you see we get the gate signal. The relay clicks and we're able to move the axis. Now let's check the e-stop. Yep, nice. The e-stop LED illuminates and the state matches in the UI. Because of how we've configured our machine in LinuxCNC, the enable signal goes to false and the charge pump stops. So there's no lockup state on the safety module. Resetting the e-stop therefore doesn't start the machine up again. It just puts us back into a state where we can start up the machine. Let's check what happens when we don't send the e-stop signal to LinuxCNC but only to the safety module. I'm disconnecting the e-stop switch from the e-stop input on the parallel port. Now when the e-stop button is pressed, the relay still switches off and depowers the motor drivers, but LinuxCNC doesn't know about it, so it's still sending the charge pump and enable state, and our lockout mode is active. To get the relay turned back on, we need to manually e-stop in the UI, and now the lockup is cleared and we can restart the machine normally. Let's test the delay circuit. If I reconnect the e-stop to LinuxCNC and turn the machine back on, let's power cycle the safety module. For about half a second after starting, the safety module acts as if it's in the lockout state. This prevents bypassing the module by power cycling it. So everything works as we expect it to. I'm not going to stick this breadboard in my control cabinet though, so let's move on to getting this manufactured. I'm planning to use this kind of modular DIN enclosure. They have clips inside for 3 or 4 layers of PCBs and have standard sizing for screw terminals. I'm going to use a slightly smaller one with 12 terminals. Because my layout gets a bit complicated, I used a 4-layer board, which are a bit more expensive, but it made the routing so much easier. I have 2 internal ground planes and signal and power routing on the top and bottom layers. Because I have multiple PCB positions in my enclosure, and because I'm already paying pick and place fees for inverters and NAND gate ICs, I added a couple of additional boards. This middle board plays an obnoxious 2-tone alarm whenever the e-stop or lockout states are active. It uses inverter ICs to set up 3 oscillators, 2 for the different adjustable tones, and 1 to bounce between them. The top board has status LEDs and a mute button to stop the beep if it's annoying while the module is on the workbench. This switch acts as a toggle using a little circuit also built with inverters. The top board connects to the middle board using an aligned pin header, and the middle connects to the bottom with a cable assembly. I had these made as a single sheet to cut on myself. Although the PCB fab did offer to separate them for me when they saw the design, it's pretty easy to cut PCB material with my 3018 router, so I stuck with my original plan to get them manufactured as a single sheet. Here's what I got: magic chop, soldered on the through-hole components and assembled into the DIN enclosure. I think it looks pretty good. There are a couple of issues with this though. Both of them come from me rushing through changes without breadboarding them fully first. I decided to invert the meaning of the enabled and charge pump LEDs to be illuminated when those signals are not present, so that it goes through red, yellow, green states like a traffic light. However, I mistakenly took the not enabled signal from this point in the circuit, which is pulled to 5 volts relatively weakly. Effectively, this means that the LED has a much larger current limiting resistor than the other LEDs, so it lights up quite dull. I also didn't have one of these surface mounted switches to test with, and there is a bit of bounce in it that makes it quite difficult to correctly interact with the toggle mute circuit. Neither of these issues are really critical, and the module otherwise works correctly in every way. However, my inner perfectionist won't let me live with that, so I redesigned the middle board to handle every input and every LED with an AT-Tiny 84 microcontroller. This also lets me do a few more interesting things, like having a splash sequence and startup tune, playing different tones for e-stop and lockout, or even, maybe not. One little trick I used here: I was right at the number of I/O pins for an AT-Tiny 84. I did consider low-level programming to turn the reset pin into a normal input, although that makes reprogramming a little bit more involved. And then I realised I could just use the reset functionality as the mute function. So during setup, we checked to see if we were reset, and if so, skip the splash sequence and ignore any current lockout or e-stop state. Once those states clear though, they can trigger the buzzer again. In theory, we could have done all of that with discrete logic, but I'd really rather not. The reason to use discrete logic for the safety features was to keep the design logically simple and verifiable, and those constraints don't apply to flashing LEDs or playing buzzers. Doing these superficial things with a microcontroller really makes a lot of sense. The new middle section hasn't arrived yet, but I'm happy to deploy the new safety module in the meantime. Here it is in situ. I am running out of space in this cabinet, but I have a few solutions to that. While I was designing the safety module, I also made smaller versions of my limit switch aggregator and the parallel port pin breakout, so I'll swap those in when I need more space. The last part to build or buy before I'm finished with the control cabinet is something to turn the spindle on and off and control its speed. However, that's for another video. Whatever I use for that will be switched on and off using the other output relay pole of the safety module. That concludes this video. The goal was to make the machine safer during startup and use, and I think that's been achieved.